the fabric and handing out lids and P keys and all that good stuff. It is configures our routing. It's got robust routing algorithms, we say, congestion, and I pulled this right off of the public marketing. Congestion avoided via fine-grained dynamic adaptive routing. Basically, we have routing algorithms that make the path through the fabric smart, is what that comes down to. And all in a goal of reducing congestion in the network. We also have a robust set of tooling. If you go on to a server that has our stuff installed and just type OPA tab, you'll see a whole bunch of commands that can be used to manage the fabric. We're also looking at how we can leverage some other open source and industry accepted tools to help work with our fabrics as well going forward. So what's most interesting probably for you guys here is the messaging support that we have. So PSM2 is, I said it's riding off into the sunset. PSM2 has served us well for, it's got over 20 years of development behind it. We are moving forward to a libfabric, the OFI, which is the Open Fabrics Interface, non-proprietary approach. We have a native provider in there called OPX. I was here 2 years ago, I think, and talking about OPX itself. Doug will probably have lots of information on that as well. It's a provider that's designed around our hardware, as opposed to the way that the PSM support was put in originally, which basically just called off to the existing PSM2 library. This is a native embedded in the fabric. The code is highly optimized. We were able to get really good performance improvements even on the OPA 100. So same hardware, just by making software changes. And I shared those results previously. It is very actively developed. We're very active in the community. And so it is open source and it's adaptable. So it can be modified, with you guys' help as well. So since I focus on the adapter, I'm going to talk mostly about that. If you got questions about switches or cables and that kind of stuff, we could certainly get you in touch with the right people. Some of the technical highlights here. So our 100 gigabit adapter was known as Wolf River. Intel had this thing about not releasing code names and stuff, but that leaked out long ago. It's on Wikipedia at this point. Everybody knows. We don't care about names so much. And we need a name in the code to call this stuff. So I'm telling you that the chip is now called Jackal River. That's our 400 gigabit. And it brings forth a lot of the technology that we have in the 100 gigabit, just bigger, faster, better. There are some new things, and we'll talk about those. Specifically, we do still continue to take advantage of the 16 DMA engines. So this is what brings data into the card, as opposed to having the CPU move the data. Generally for your larger transfers or smaller transfers, and we have programmed I/O, PIO. We increased the number of contexts that we have in Wolf River to 240 in Jackal River. We've also increased the memory on board from 1 to 4 megabytes for the transfer buffer, the send buffer. Similarly, for received contexts, we have 240 of those as well. One of the big changes is we're going full support for 16B packets. So 16B packets, that 16B refers to the number of bytes in the header. We've traditionally used what we call 9B packets, which is a 8-byte InfiniBand header plus an extra byte that the hardware strips off for us. But we're moving towards 16B. We will still support 9B packets, so we'll still support verbs and IP over IP, all that stuff. But 16B allows us, for one, to use a larger lid space. We get 24 bits for the lid versus 16 bits with the normal InfiniBand packets. And it is how we can encode our adaptive routing stuff. The P key table, so this is important for people that are into your SE Linux and the multi-label security. We only had 16 P key supported hardware before. We've increased that just a little bit to 1024 P keys. And the receive descriptor, so this is basically what describes the packets as they come in, or describes where the packets should go to. We've increased from 65,000 to 131,000 in Jackal River. We do still support 8 VLs plus VL15 for management packets. And one of the big new features that this chip supports is native PCIe SRIOV. So there is a lot of code changes that are coming down the pipe for this. One thing that I find really cool is we actually have loopback ports built into the hardware, so we can talk from SI to SI, so from virtual machine to virtual machine over these loopback ports and not actually have to go out onto the fabric. The other big thing that we have is this integrated C port processor. So I think C port stands for configuration port or something, I don't know, but it's a micro that's embedded on our board, and it handles the fabric management, it handles link negotiation. A bunch of stuff that the driver used to have to do is now done in firmware, so the driver can do its thing. Our receive side matching, these are our SM rules. These have increased from 4 to 32. I got a number of ideas for how we can exploit this. We are using it for certain things, but there's still going to be a number of these left over. And this is, one way that I would like to engage with you folks on is, how you can take advantage of these. And I'll talk more about these. And then there's a whole bunch of other bells and whistles in the hardware that, but this is I think the most important ones. It's bigger, faster, better. So that was kind of the spiel on what we have and who we are. So now we'll actually get into the technical aspect of things here. So you've heard me mention PIO, the programmed IO. So this is where we use the CPU to copy data. So be able to set up a DMA transfer for DMA engines, there's a cost for that. There's time it takes to do that. And at some point, it's just more efficient to let the CPU move the data. So that's when you would use PIO. So the driver sets up these things called send contexts, which is for applications to actually be able to write their data into the card. So the user's applications, so the OPX or even libPSM2, whatever, they have direct access to the card through memory mapped registers. So this is true kernel bypass. So once the kernel sets things up and hands control over to the user application that asks for a context to be created, they have full direct access without going through the kernel. There is a credit-based mechanism that is used to be able to know when a packet has been sent and when it's okay to overwrite what's in the send buffer. So the user and the hardware work in concert to be able to know when that packet has launched. From the kernel's point of view, which is setting this thing up, the send context is just an abstraction for the send engine, which is on the hardware. I said that we enable multiple order streams of packets, and that's what it does. So we've got 240 of these, so you can have 240 streams of packets at the same time. They are ordered within each send context, so the order that you write stuff into the send buffer is the order that it's going to be launched. Once it's launched and goes out onto the fabric, it could take different paths through the fabric depending on the routing and all that other stuff. But you at least have control over what gets launched. There is no ordering between them. So there's arbitration that goes and chooses which which VL to launch packets on. So depending on what VLs and what other QoS mechanisms you have in place will determine the order that the send contexts will arbitrate. So this is kind of a picture of what the a send context looks like. There's a whole bunch of stuff in there, but at its core, there's an address and a size, and then a bunch of register pointers for credits, and there's a number of locks that coordinate access to all this stuff. So I mentioned that this is for your small messages where it's better for the CPU to move data. There is an issue here though that with the trade-off, it does cause contention on the PCI bus because you're using the CPU to go out and move data across like that. There's also no ordering between contexts, like I mentioned, but there's no ordering with SDMA engines. So if you have an application that's doing PIO and SDMA, you have to be careful that just because you wrote something in the PIO buffer and then SDMA doesn't mean that the SDMA is not going to launch first. So that's one thing to keep in mind when actually working with these. For allocating send context, the user space is going to call into the kernel, and the kernel is going to set everything up. By default, the kernel keeps the number of send contexts for itself, so a number of those 240 are reserved for the kernel. By default, we keep 2 per VL plus 1 or 2 for VL15. This is so we can always serve all VLs. There's also a couple that are set aside for verbs and our optimized IP over IB. Cport also consumes a couple. And the majority of the contexts are available for user space, and this is actually configurable. So by default, like I said, we keep 2 per VL, but you can change this and dedicate more context to user space. So if you're not doing verbs, you can give more context to user space, certainly. The user gets a context by opening up a file descriptor to our character device. There is a whole bunch of contention with this upstream, and eventually it's going to be going away that we use currently. But at the end, there will still be a character device that is opened by the user, and they will get some kind of identifier. Right now, it's just what. So context is a very overloaded term. We have receive context, we have send context, and then we have user context, which is the representation of a user process. And one of the issues is, what do we do about these CPUs that have gigantic number of cores? And we are seeing CPUs come out with tons and tons of cores, and that is a valid concern, and it is possible for user processes to share contexts, and that's totally up to software how that sharing is facilitated. We do have a mechanism for sharing context in PSM2. We're also working on one for OPX as well. When filling the send buffers, so packets within a send buffer are going to be ordered up until it launches, like I said before. Send buffers are divided up into send blocks that are 64 bytes in width, and the start of every packet for us has this thing called a PBC. I think that's per buffer control. It's basically a 64 bit blob that has information about the packet for the hardware to look at and figure out where the packet basically has to be able to figure out where the packet ends for the most part. Yeah, so we have this credit return song and dance that has to go between the user and the hardware, and it's up to user space to do the right thing there, because again, this is kernel bypass, so the driver is hands off for this stuff. So it can be difficult to program in this kind of model, but that's the price you have to pay to be able to have unfettered access to the actual hardware. SDMA is the other way of sending data, like I had mentioned. This is for your larger messages because it does require some setup to be able to program the SDMA engines. We do have 16 of these things. They have to be programmed by the kernel because DMA engines, because there's only 16 of them, it's a shared scarce resource. This also means we don't have to do the virtual to physical translation in the hardware, and we don't have to do it in software either. So we let the kernel take care of doing that stuff. In the host memory, we have these things called an SDMA ring, which is just a normal ring buffer where the user's buffers live. The PBC is really what starts it. There's no order that has to be tied between the way things are laid out in host memory and the way things are laid out on the HFI. So this is your scatter gather. You can have things scattered throughout the host memory, and it's how you write them to where you write them at in the HFI memory that's going to determine how the packets are assembled that go out on the wire. The user interface for the kernel and right now is the user basically gives us us being the kernel, gives us a template for what the header is going to look like. So for PIO, the user has to write everything for the packet, has to create the headers and everything and put those in the buffer because it's kernel bypass. For this, the user just gives us a description of what it wants for the header. The driver is going to take that data that's coming in, it's going to packetize that and load up the SDMA engines on the hardware to go and pull the data in. It's important to note that the kernel is not copying data here. It's copying the pointers to the data. It is getting IOVEX from the user, and we're just copying what's the content of those IOVEX so that we can pull things off efficiently. The kernel then has to pin memory, and so it pins memory, it builds the packets, and then it returns to the user. So while it's pinning memory and building packets, it is blocked currently. There are ways around that using something called IOU ring. Users can actually have full asynchronous ways of doing file descriptor operations. And but in general, we return before the send happens. So once it returns from this call, you know that the stuff is going to the packet is going to launch. Now that doesn't mean that the packet's going to go out. It could still have an error and fail, but you'll get an error that tells you that the packet failed. And we use what I call a scoreboard. So that's how we convey the completion information to the user, and lets it know if it's been sent or if there was a problem or whatever. This is a picture of what SDMA looks like, and like I said, that we've got these IOVEX that point into the physical memory, and those IOVEX get copied into the kernel, and the kernel loads up the descriptor ring with the information about those buffers. So we're not actually copying, but the SDMA engines now on the card are going to go pull that stuff in and be able to send the packets then. So that's the send side. We have for the receive side, we have what's called eager receive. So this is kind of like the PIO method. There are receive contexts, 240 receive contexts. The user gets direct access to these as well. There is no architectural requirement that receive context map to send context. So you could have one receive context and 100 send contexts for an application if you wanted to. There's nothing that prevents that. Commonly, though, and what I think OPX does and what PSM2 did do and what we do for verbs in the kernel is we tend to associate a one-to-one mapping. Whenever you allocate a send context, you get a receive context. But for your applications and for your libraries, this might not be what you want to do. You might want to be able to have a many to one mapping or something. And architecturally, that would be fully supported. The other way of receiving data is what we call expected receive. This is the TID, or the tagged identifier, and basically this is your actual direct data placement. This is where you get the RDMA from. So there is our KDEF headers, and has information in it that describe TID regions, and those regions are where data is going to be placed. So right now in our libraries, we use a common rendezvous protocol, the ready to send, clear to send, and that's how you actually get data to land directly without having to copy things in and out. So important concept for working with these two different types of receive is how do things know where to land? How does it know whether it's going to be an expected receive versus a eager or whatever? So basically the hardware is going to look at the packets as it comes in, and it figures out what it is, and it classifies it as one of these 5 types. So type 0 packets are the expected receive, and there's a field in the header called TID control, and if that's 0, then it's going to look at the Q pair field and the BTH. If you're familiar with InfiniBand packets, then that would make sense. If not, you would have. I don't have a good picture for what the headers look like, but I'm sure that's fairly easy to find. But so there's a destination Q pair number field in there, and that's what helps us figure out what the context is going to be for whether it's expected versus eager. So eager is where the TID control field is 0, and again looks at the destination Q pair field in the BTH. For type 2 packets, these are your InfiniBand packets, so normal verbs traffic or IP over IB. There is again, the destination Q pair field, we use that field directly, and we have a table in the hardware that maps Q pairs to their respective receive contexts. Type 3 packets are errors, so if the hardware gets it, the CRC is bad, or any number of other things that's wrong with the packet, they get flagged as an error. We also have a type of packets called bypass packets. These were predominantly used in Wolf River for 16B packets. So the Wolf River only supported 9B packets in hardware, we say. 16B packets were it means they bypass the chip. So it will land the packet, and it doesn't check CRCs, it doesn't check anything, it lands and it just sits there. It has to be copied out to where it needs to go. That's in Wolf River. It's not necessarily for Jackal River. And that just maps to a single context, as does the error. There's a default context that you set up, and that's what will get all your errors. So I mentioned earlier about the receive side mapping rules. So think of this as an override for determining where data is going to land. It's targeted for eager receives, but it will work on, if something comes in targeting as an expected receive, the hardware is going to reclassify it as an eager receive. And we did have this in Wolf River, where we only had 4 instances. And in Jackal River, we've moved this to 32. We are also able to go much deeper into the packet now. We can look into the packet 1024 bits. Before, I think it was maybe 128. I don't recall for sure. I have to look at the code, but we definitely are able to go much deeper into the packet. Each RSM instance has what we call match units. It has 4 match units. So these are things parts of the packet that it can look at. And then you program these things, and that's how it will choose where to land. In this So in the packet reception pipeline, this actually happens before all the other stuff. So like I said, this is an override for what you have set. And there's currently no user API for this. This is something that doesn't exist on other hardwares as far as I know. Um, but it's something that I think is advantageous and would be interested in hearing you guys' thoughts on how this could be used. Anybody that's been through any of my talks before, I always have some kind of a call to action, and that's kind of what this is for this one. Um, how could Mbappage take advantage of these receive side mapping rules? What could we do with this? And what would that look like? What would the interface look like to be able to use that? So this is where, I said, this is where our dedication to open source shines. And it really is. We really do want to hear from users and understand, what would be useful to be able to exploit these. Anybody that's ever tried to upstream code to the Linux kernel, especially user interface code, knows it is a very hot button topic. It is very contentious and just flat out hard to do. So before we start proposing APIs and putting stuff out there, we want to know what people really want, and we really need to collaborate and have our story straight, when we go to the community with this kind of stuff. I had alluded to, we have this thing called C-port in the hardware now. And what this guy does is it handles all of the firmware. So before the Wolf River driver, it had to handle loading and unloading firmware. It had to do a PCIe Gen 3 bump because the hardware came up in Gen 2. It had required special firmware to go to Gen 3. All that stuff has gone out the window. The card just comes up in Gen 5. And now C-port is going to handle loading firmware, upgrading firmware. Makes my life much easier. It is also going to handle the link negotiation. So LNI is a very big part of just getting the thing to show up on the fabric. There's a lot of stuff that has to happen basically to get a link light to come on. It's something that as software engineers you don't really have an appreciation of, because you don't pay any attention to it until, oh, there's a link there. Okay, that means I can actually use the device. There's a ton of stuff that has to happen to be able to bring a link up. And whereas we had to do that in Wolf River, now we've pushed that down into the firmware to handle all this stuff. MAD packets. So these are your management datagrams, and this is the stuff that assigns lids and P keys and all that stuff. But what it also does is provide performance data, telemetry, counters, and if the driver is busy servicing requests for performance data for packet counts and things like that, it can't be doing what it's meant to do, which is set up jobs and work on behalf of the user. So pushing this stuff down into C-port means that we don't have to deal with it in the kernel anymore. And like I said, the driver's free to do what it needs to do for the user's job. So GPU support, we do plan to support NVIDIA and AMD GPUs with this. So how do we take advantage of the GPU hardware? I've got a couple little pictures that'll show that here in a second. I talk a lot about open source and being in kernel and into the distro, and this is one of those aspects where I just kind of have to hold my nose and go with it because it stinks. Because of the GPU licensing and driver availability, we can't put our GPU code in the mainline Linux kernel, so we have to have our separate version that I mentioned before. There's a technology known as DMA buff. This is it's an open source way of moving data between PCI devices, things that are hooked on a PCI device. that only gets us halfway there. So even if everybody supported that, we still need to have the driver support in the kernel, because the kernel people are never going to let us include calls to proprietary drivers. And there's actually changes that are constantly going in to make that harder and harder to do. We ran into a problem recently. Yeah.
The question is about DMA buff. With let's say earlier we used to have like GDR copy, IPC, like GPU direct RDMA, bunch of things. What of these does DMA buff help to let's say alleviate or replace?
Say that again.
So the DMA buff technology inside the Linux kernel, which is coming up,
Right.
what does it help replace? Does it?
What does it help replace? So this is, yeah, the GDR copy stuff. So this is, yeah, it would be like the GDR copy that NVIDIA had. Yeah. And even GPU Direct as well, I guess, actually all of it. So DMA buff, I don't think it has to be between hardware. So GDR copy is more, that's software to hardware, right? And then the GPU Direct, that NVIDIA calls it, that's device to device. So it would be probably more for that, maybe.
Okay. One follow-up question. Does DMA buff allow, or DMA buff APIs allow us to use the DMA engines on the host for host-to-host transfers as well?
It lets you use on DMA engines on the GPU device.
Okay, but
not the other ones. Yeah.
Okay.
Ones on our thing.
Thanks.
Yeah. So like I said, it's, that only gets us halfway there. We have to have the drivers in the kernel. So here is how we do PIO sends with GPUs, and basically this is up to the user to figure out. We don't care in the kernel, because this is kernel bypass. So PIO is the driver stays out of the way. So the most efficient way is using the GPU vendor's device copy, GDR copy for NVIDIA. AMD has a similar API, I believe. For PSM2, we had our own version of GDR copy that predated the access to the NVIDIA one. And PSM2 continues to use that to this day. But libfabric does not. Libfabric uses, or our OPX thing in libfabric uses whatever libfabric does, which is, I believe it uses the NVIDIA one, and it has this abstraction called HMEM, I think that's what it is. But the important thing for the driver and for kernel is this is just a PIO send to us. It is completely out of our hands. SDMA, this is a different animal, so to speak. So this is where the user has to tell us, it has to tell us, one, that this buffer is on a GPU, and then we have to use the GPU library to pin those pages down to be able to SDMA the stuff. So this is the problem with the upstream. Where we can't call off to the GPU functions to be able to pin data.
So one follow-up question here. One of the challenges with, let's say, GPU direct transfers is detecting whether a buffer resides on the host or the GPU, which is an expensive call. Have you implemented some sort of a cache or, let's say, some data structure like that to reduce the number of driver calls to detect if a buffer is a GPU or a host buffer?
So the user tells us that. So we in the current API, there's a field in there for the user to tell us if it's a GPU and what GPU it is, tells us whether it's NVIDIA or AMD. So that determination of figuring out what it is pushed up into the libfabric to figure out.
Yeah, and so at the libfabric level, we do exactly that. Yeah, we use a cache for our pinned buffers so that we can reuse them and avoid another registration call.
Okay. So as I understand it, it is up to the user to do the determination and tell the OFI. Is that right?
No, the OFI we can figure it out in our libfabric provider. So it's Denny's user.
Okay.
But our user, like our application middleware, doesn't have to know as long as they implement the API.
Okay. Let's say for some reason, if the application and middleware needs to know this before handing it over to OFI, is there some way we can reuse the, let's say, cache you have implemented for our purposes?
No, but we should make one. It's a good idea.
Yeah, thanks.
Yeah, let's talk about it. Thank you.
Okay, so I'll mention a little bit about the upstream here. I know think I'm running up on time here shortly. So I talk a lot about upstream and working with kernel.org. That's what I do. It's what I'm passionate about. So for upstreaming OPX, it tends to be a little bit of an easier path. We are very active contributors there. We do maintain our OPX provider. And we have a good relationship with those people. Upstreaming to the kernel is a totally different story. Especially upstreaming major changes is not easy. It's anybody that has ever tried to submit patches knows this. Now the good thing is here we've been doing this for a long time and we know how not to do things. When we first upstreamed HFI1, it was absolutely destroyed by the reviewers. And we ended up having to put the driver in this section of the kernel called staging, which, okay, it sounds like it's a good thing. Driver just goes and gets worked on when it has a bunch of to-dos. Well, that's also means it's free reign for everybody that wants to get their name in the Linux kernel. So we get flooded with patches to do trivial stuff. Change the way the format of this comment, or, and a lot of it is fairly innocuous, but we ended up getting things that actually cause bugs where, somebody fixes a spelling correction in a string and now, we've changed the size of something. And it was a nightmare just for that. It's also, now you have to deal with two different subsystems. It's a completely different maintainer. So based on the experience that we had with that, the RDMA community kind of came together and said, we'll never send another driver to staging. So anyway, I just went to pull this out to see, when we actually went live in the kernel. So, and this was all the way back in 2016. So we've been doing this a long time, working with the community. So I'm not saying that it's going to be easy to upstream all these changes, especially with SRIOV, because that is a major change. But we've done it. We know what we're doing. So we're fairly confident in being able to actually get that done here. So what is our plan for actually doing the upstream? It's not going to be HFI2 like I mentioned before. It's one driver. And this ends up making sense because Jackal River is based on a lot of the same concepts that Wolf River is, but is bigger, faster, better. So since and actually I mentioned to the maintainer before, we called it HFI1 for a reason when he was asking if we were going to put another driver. And I said, well, yeah, it's got HFI1 for a reason. And he freaked out and said, please, God, no, don't do that again. So we are sticking with one driver. And this benefits us because it's already in the kernel. It's already in all the distros. So when people download the latest Red Hat after we've upstreamed our stuff, they'll have all of the support and it'll just work right out of the box. You don't have to go download special packages for our stuff. It's just, you get it by default. We also don't delete anybody else's drivers like certain ones do. QIB is our previous old InfiniBand. I think Linus told me it was grandma's RDMA before we should get rid of it. So it is finally going to go away, but I swear every time that I go to actually remove this thing and send the packet or send the patch to the mailing list, somebody comes out of the woodwork and has a question or is trying to run QIB on some old cluster that they found in a closet at a university somewhere. but I'm determined to finally kill it off here and delete it from the upstream kernel. This is just showing a picture of how people actually get our code. We send our code to kernel.org, like I've been saying, and that goes to the world and eventually gets picked up into the distros. Well, then we turn around and we use that as the base for what we package up and bless and give to our customers. So when I talk about the GPU code, we take the distro's driver, which is already full of our code that we had submitted upstream, and then we glue on top the GPU code. Previously, what we used to do was we had a separate out of tree fork of the driver, and we continually updated it to support new distros. Turns out this is much, much faster and easier. Whereas now we don't have to backport other things. We just have to take and leverage what the distros have done. So this is just a summary of the major changes that we've had to make to be able to support multiple chips with a single driver, changing registers, moving their offsets, even if they have a similar function between the chips is something was painful. We have to be able to figure out how to do. I talked about having multiple ports now. The C port management model is totally new, and that took some doing. The UAPI changes, I kind of alluded to this a little bit. The kernel community does not like the fact that we have our own private character device that we use, and that is going away. We're going to leverage the character device that is owned by the RDMA core, and then obviously we're having even more GPU support. So there is this other driver that sits out there called RDMA-VT. One of our main problems with HFI1 and QIB was there was a lot of code duplication between the two drivers. So this was a driver that I wrote to solve that. But now, since we're not going to have two drivers that need to share a software verbs implementation, we don't really need this anymore. But I have talked to the maintainer, and we kind of agreed that we don't have to get rid of it. So RDMA-VT is going to continue to stay. Maybe someday if we run out of things to do, we'll collapse it back into one driver. But for the most part, this is completely invisible to people that are writing applications like yourselves. So the overall status is that the kernel code is coming soon. It'll be on the mailing list, and the CN5000 is coming out later this year. We do still have Open 100. It is still fully supported. We have lots of customers worldwide, including some very large deployments. We're very active in developing it. We recently added AMD GPU support, and we recently also added a backwards compatibility layer for working with the new way of just adding stuff on top of the distro that I had talked about. And that's out now too.
So